Deep neural networks, or DNNs, are found in many modern applications because of their powerful ability to learn from high-dimensional data, like images and natural language. In order to use neural nets for custom applications, they must be trained and tuned, a process which can be challenging to debug. One significant challenge of this process is that errors are often silent. For example, a model can have random chance accuracy during evaluation, meaning it hasn't learned any patterns from the data. In cases like this, there are no messages that directly inform the user what errors led to this condition. Models can also produce unexpected output during training, which can be hard for non-experts to interpret, such as when loss values increase rather than decrease, or when nans appear in the output. While experts can use tools like TensorBoard to inspect the behavior of their models, non-experts often think of DNNs as black boxes and lack strong mental models to interpret their results. In our work, we identify three critical gulfs of the DNN debugging process: mapping from symptoms to their root causes, choosing a strategy to address the underlying problem, and mapping from the strategy to a concrete code implementation. We introduce Umlaut, a Python library and a web application which supports users through these gulfs in the DNN debugging process. Umlaut runs automated checks of a deep learning program's structure and behavior and guides users through explanation-driven error messages which are tightly coupled with visualizations and code. Let's take a look at an example of Umlaut in action. Here is a typical program for an image classifier written in the Keras framework. The model we create classifies 10 kinds of images, such as cars, airplanes, dogs, and birds. The program defines a model and trains it on the CIFAR10 dataset for 10 epochs. After training, we see our model isn't able to learn any meaningful patterns from the data. Our 10% accuracy is the same as random chance. Let's attach an Umlaut client to see what's going on. Running the program again, we see Umlaut emits error messages to the command line. Let's open its web interface to understand what these are. The Umlaut interface shows us a timeline of raised errors on top, error messages on the right, and standard visualizations of model loss and accuracy on the left. This critical error is telling us a softmax calculation is missing before the model's loss function. The error explains the underlying theory, suggests potential solutions, and includes a code snippet to implement a suggested fix, an additional argument to pass into our Keras loss function class. Let's make the change Umlaut suggests to add a softmax calculation. Now, our model seems to be learning well. However, Umlaut is warning us that the model seems to be overfitting on the training data. To see if this error represents a trend, we click it, which annotates the plots and the timeline. Let's do what Umlaut suggests and add dropout to our model, a well-established technique in the literature to reduce overfitting. With dropout added, the overfitting warning is now gone, and our loss is going down smoothly. There's only one error left, indicating we forgot to normalize our data. Umlaut includes the program context during runtime, telling us the model received an input of 255, which is outside the typical range from -1 to 1. Let's make the change and run Umlaut again. Our model now achieves a 76% test set accuracy, and Umlaut shows no errors, a satisfying result. In the Umlaut interface, error messages are linked to annotated visualizations of model loss and accuracy, helping users recognize symptoms and map them to their root causes. Umlaut error messages help users choose a strategy to address the underlying problem with explanations of their theory and program context. To map from strategy to a concrete code implementation, Umlaut errors include code recipes, linked to Stack Overflow and documentation, and references back to the source code. In order to run heuristic checks, the Umlaut client monitors several components of the deep learning program runtime. Static checks, such as checking for activation functions, are run on the model graph and source code before training begins. Dynamic checks, such as checking for overfitting, are run during training. In addition to static data, they capture model input and output and training metrics. When a heuristic check fails, it populates an error with the relevant program context. This data is logged by an API request to an Umlaut server, which renders the web interface. To evaluate Umlaut, we conducted a within-subject study with 15 participants. Their task was to debug 2 image classification programs with different sets of 3 bugs introduced. Participants were asked to find and fix all the bugs in these programs, alternating with and without Umlaut in counterbalanced conditions. When using Umlaut, participants found and fixed significantly more bugs in each program. Please look at our paper for details. In summary, we created the Umlaut system, which helps users find and fix errors in their deep neural networks. Umlaut helps users overcome critical gulfs in the deep learning debugging process by linking explanation-driven error messages, annotated visualizations, and code in the same interface. We believe Umlaut presents many opportunities for future work in supporting users throughout the process of developing, debugging, and deploying deep neural networks.